present some recent work about the trade-off between the cooperative communication and localization in vehicular networks. So let's start by the context. We want to localize the vehicle. We can simply use the GBET, but we all know that GBET is problematic in some cases. For example, GBET may not be available in some common environment like urban canyon and tunnels. It's only fine for day one applications such as networking or route guidance. Even though latest versions like RTK or PPP are very precise, but they still have some specific issues like require reference station, conversion time or condition, and also the service continuities. So furthermore, day 2 applications like road hazard warning and the autonomous driving or the safety of vulnerable road users require very high accuracy regardless of operating condition. So we need to find a new, more advanced, context-aware and highly accurate localization alternative with constant quality of service. So let's move to the motivation. To localize the vehicle, conventional approach use the satellite or the infrastructure like cellular base station or the roadside unit to perform the multilateration. They refer to non-cooperative localization. However, we all know that vehicles are never alone, leading to the interest in cooperative localization. For one thing, our GPS may be bad, but the other may not. So we expect benefits from the heterogeneous GPS condition to the B2B cooperation. For another thing, we have the vehicle broadcast its position and the timestamp in the cooperative awareness messages periodically to maintain the local dynamic map for many purposes. So we can simply measure the RSI of these packets, so we can know the range dependent information to the neighbors. And at the end of the day, we can fill all available information in the context-aware fusion to get the best accurate ego position. We call it as the opportunistic cooperative localization because it requires no additional hardware. So consider vehicle I at time PI. It has the onboard GPS position, the belief in the receive cam, and the B2B RSI of the packets. And the goal is to estimate the ego position given all information from the beginning up to the current instant using distributed particle filter. Remind that the particle filters is the Monte Carlo approximation of the Bayesian sequential Bayesian estimation. And why distributed particle filter? Because it supports any nonlinearity and any distribution. However, it requires high number of particles, causing some difficulties to broadcast the positional information to the neighbors. And it generates heavy communication load to the channels with limited capacity. So let's summarize the challenges. First, limited cam size cannot carry heavy particle cloud up to kilobyte. Secondly, limited capacity. Usually we have 60 to 70% of the channel for cam. So, for example, 100 particles, we can check the channel definitely. Furthermore, in case of congestion, the SC DCC will reduce the rate to 2 Hz, and we expect the localization accuracy degradation because we receive fewer beliefs and measurement. So we solve the problem at the signal processing level approach to reduce the size of particle information in the single cam by using the parametric method approximation. We also solve the problem at the protocol level approach to adopt smart transmission according to the neighboring need by introducing jointly adaptive transmission payload rate and power. Finally, the approach can be combined to the single solution. So let's start with the parametric method approximation. The idea is very simple to approximate the non-parametric particle cloud by a priori parametric Gaussian mixture distribution by using the maximum likelihood estimators. In our study, we consider only the unimodal or bimodal Gaussian. We do not consider higher model distribution because we believe that fully localized node cannot improve the accuracy of the others. So at the illustration, we have the unimodal particle can be approximated by either Gaussian unimodal Gaussian or bimodal Gaussian, and so is the bimodal particle. So let's summarize the method approximation by the simplified example. So as you can see, vehicle I firstly approximate it the kilobyte particle based belief by a Gaussian mixture distribution, then only encapsulate a few bytes in the cam to crosscut to its neighbor, and receiving vehicle J extract this parameter in the message to identify the distribution. Then it can draw the sample from this distribution to reconstruct the particle class using for its own particle filters. So let's move to the transmission control strategy. Remind that we use the cam to update the neighboring position and to get the RSI measurement. So to reach the best accuracy, we need the 10 Hz neighboring belief and 10 Hz RSI or 10 Hz cam in short, because we can only transmit cam at maximum 10 Hz. So, but we do not always transmit the cam at 10 Hz due to several reasons. For example, highly constrained vehicular mobility will cause some correction effect, and we are also constrained by the SCDCC. So our proposal is to send the cam at a very low rate, let's say 2 Hz, to provide the belief, and rely on the correlation effect to make the belief prediction. And we also send the tiny cam with reduced header at maximum rate 10 Hz to provide the RSI measurement. And by doing this, we can have 10 Hz belief and 10 Hz measurement, but we don't need to transmit the 10 Hz cam. So some benefit of this proposal is the compatibility with the SCDCC, provide boosted localization accuracy and easy for implementation. So when we transmit 10 Hz cam, we get precise belief but high channel loss. When we mix the normal cam with the tiny cam, we reduce dramatically the channel loss, but trailing a bit the belief accuracy. However, we claim that the accuracy degradation is small because we only predict in short term, and so it can very precise due to the highly correlated mobility. Then because the tiny cam is used for to get the RSI measurement, we don't need to broadcast the tiny cam to all the neighbors. We just broadcast it to the locally. So let's see in the figure this is the vehicle, the central vehicle 8, and this is the error eclipse when this cooperate with one hot neighbor and with all the neighbors. So we can see that there is no difference in the accuracy. This means that the other neighbors are very uninformative. So let's move on the simulation setting and scenario. We model the 3-lane highway model when 15 vehicles are running in the same direction. We use the Go-Markov model to generate the vehicle trajectory. Some other important parameters are summarized in this table, but let's focus on some interesting one. For the rate control, we use 10 Hz for congestion-free condition and 2 Hz for congested one. For the payload control, we consider 300 bytes for cam and 30 bytes for the tiny cam, equivalent to the ping vehicle buckets. For the power control, we use maximum power to broadcast the cam, while use only -5 dBm for the tiny cam to reach only local neighbors. So we now compare different message representation. Besides particle, 2D position can be approximated by either UD model Gaussian or B model Gaussian, and 2D velocity can only be approximated by UD model Gaussian. So in terms of localization, we see no accuracy degradation. It means that in our problem, when we have enough neighbors, the posterior distribution is rather compact and simple. In terms of communication, we restate that we cannot have particle-based cooperative localization without message approximation. So since we are in highly mobility vehicular network, the algorithm must be fast and low complex. So when we use high model distribution, we have to estimate more parameters, leading to higher required number of iteration. So we glad that in our problem, unimodal Gaussian is sufficient to reach a required level of accuracy. So let's move on the result for the transmission control strategy. So this is the performance when we use the standalone GPS with filtering. This is the performance when we for the cooperative localization with 10 Hz cam in congestion-free condition. But in the congested one, the SCDCC will reduce the rate to 2 Hz, so we also lose the accuracy. And then by additionally sending the tiny cam still with the message approximation, we improve the accuracy approaching the congestion-free scenario. And finally, we incorporate with the message approximation for more realistic setting. And we study the impact on the channel load. So as you can see, Sending 10 scam costs 40% of channel loss in our simulation. When SCDCC is triggered, it only costs 8% of channel loss. By sending additionally the Tanicam cost 0.4%, we improve the accuracy. And now that leads me to the conclusion. We claim that if we want to use the particle-based cooperative localization, we need to have the message approximation. Secondly, unimodal version is sufficient to reach the required localization accuracy. In the contracted scenario, our proposal maintain the high precision service up to 22% with regard to the case when SCDCC is triggered, only cost 0.4% of channel loss. In the congestion-free scenario, we significantly reduce the communication traffic up to 80% channel loss, and also the computational loss in terms of the number of message approximation procedures up to 80%, and with very slight performance degradation, 8% of location errors. And from perspective, we will study more efficient context-aware transmission control by considering the real mobility models, the vehicle densities. We also consider more realistic mobility traces to analyze the effects on the transmission control, and also more complicated B2B propagation channel to study the effects on the message approximation. This is the end. Thank you.